Hello, AP Stat students. In 11.1, we talked about the chi-squared goodness of fit test, where we took one variable and analyzed its distribution. In this next test, the chi-squared test for homogeneity, we are breaking down two variables and we're looking at two or more samples. So we're looking at what influences what. So we're going to go back to stuff we learned in first semester, the relationship between the explanatory variables versus response variables. We're going to compare the conditional distributions of response variable for each explanatory variable. Example could be gender affects your favorite color. So we break down colors for males and females and then we compare. So you calculate conditional distributions. So breakdown for females and breakdown for males. You graph them. You describe where the differences are. We will test for any overall differences. If there are differences, we analyze what differs and by how much. So this is our follow-up. Our expected counts, what we do is you take the marginal distribution for each response variable and you multiply by the total in each explanatory variable. It'll make more sense when we do an example. For the chi-squared statistic, the degrees of freedom will be different than what it was for the goodness of fit test. What we do is you take the row -1 and then the column -1. So the categories in your row subtracted by 1 times the categories in your column, subtract 1. And again, it takes 2 or more samples. Okay. Here is what the test would look like. So in the state portion, we want to perform a chi-squared test of homogeneity at whatever significance level. The hypotheses are stated differently, and they're pretty easy actually because they're worded basically the same way. So the null hypothesis, it's always going to be there is no difference in the distribution of the response for explanatory. So in our case, it would be there's no difference in the distribution of favorite color for gender. So you can just put that here. And then the alternative hypothesis, there is a difference in the distribution of response for explanatory. Then you check if your conditions are met, and if conditions are met, then you're going to do the chi-squared test for homogeneity. So random, it's going to be a random sample or randomized experiment. The large sample, the expected value you will get by taking the marginal distribution times the total for one category and so on. I'll show you how to do all that in our example. And then the independent observations are independent or 10% rule. And then you do the chi-squared statistic, which is the same formula as for the goodness of fit. So it'd be observed minus expected quantity squared divided by the expected. And do the summation, list out at least two of the first terms. Then you calculate the p-value using the chi-squared CDF with lower bound, upper bound, and degrees of freedom. Remember, degrees of freedom, categories -1 times categories -1. Remember, the p-value is the probability of getting the chi-squared statistic if the null hypothesis is true. You compare the p-value to the significance level. If the p-value is less than alpha, we reject the null hypothesis. If the p-value is not less than alpha, we fail to reject the null hypothesis. And then we interpret those results in context. We reject the null hypothesis, so we have convincing evidence of the alternative hypothesis. We fail to reject the null hypothesis, so we do not have convincing evidence of the alternative hypothesis. And you do all that in context. Then you do a follow-up if you reject the null hypothesis. Which cells show large deviations? Which direction are the deviations in? So when we talk about which cells show large deviations, talk about your highest component and in which direction, talk about whether it's higher or lower than expected. Great, and we are going to do an example. And this takes quite a bit of time because we have to make a graph. But in Chapter 1, an example examined the distribution of superpower preference for a random sample of 200 children ages 9 through 17 from the United Kingdom. Do American children have the same preferences? To find out, a random sample of 215 U.S. children ages 9 through 17 was selected. Here are the results from both samples. So alongside the left, we have our response. So our responses are fly, freeze time, invisibility, super strength, and telepathy. So these are our superpowers. Okay. And then alongside the top are your explanatory variables. Okay, so your countries. Okay, and then you have the totals for each row and the totals for each column. And the first thing we're going to do is calculate the conditional distribution. So the conditional distribution we want to put in our table. So 54 out of 200 UK children prefer fly. And so that would be 0.27. And we're doing this because I'm going to have you graph these. And then 52 out of 200, which is 0.26. 30 out of 200, choose invisibility, 0.15. 20 out of 200, 0.10. And lastly, 44 out of 200, 0.22. Do the same thing for US. So 45 over 215 equals 0.21. 44 over 215 equals 0.20. 37 over 215 equals 0.17. 23 over 215 equals 0.11. 66 over 215 equals 0.31. All right, and so before we do anything further, we are going to construct a graph to compare the distribution of superpower preference for UK and US children. Now notice we are actually doing percent of superpowers because even though the samples are close, they're not exactly the same. So the best thing to do is just graph those. That's why I graph the percents. So we will do that for each group. So I'm going to go ahead and do UK. I'll do UK first and then I'll do US. So UK 27% chose fly. So I should do US first since it's right there. So I'll do US first. So 21. And then 20% chose freeze time. Okay, 17 invisibility. Okay, 11 for super strength. And then lastly, 31 for telepathy right here. Okay, now I'm going to do UK, so 27. And I'll do that graph, so it looks a little bit different. Okay, then 26. 15. 10. And lastly, 22. All right, and so we're doing the percent instead of counts due to the 200 and 215 counts. And if you look, it seems like the biggest difference is in telepathy and flying. Do these data provide convincing evidence that the distribution of superpower preference differs among US and UK children? We want to perform a chi-squared test for homogeneity at a 0.05 significance level. There is no difference. The null hypothesis says there is no difference in the distribution of superpowers for kids from the UK and kids from the US. The alternative hypothesis says there is a difference in the response variable, which is superpowers for kids from the UK and kids from the US. Before we go into the plan section, we want to figure out what the marginal distributions are. This is really important because it'll help us figure out the expected values. And so the expected proportion if there is no difference is the following. So what you do is you take these values right here and you would do 99 divided by 415. So you're taking that entire row of flying for both UK and US divided by 415, and that'll give us 0.24. So these are our expected proportions if there's no difference. And then do the same thing for freeze time, 96 over 415. That's 0.23. 67 over 415. That is 0.16. 43 over 415, 0.10, and lastly 110 over 415, and that gives us 0.27. These are the marginal distributions. And so what you do is you use those proportions and multiply by the sample size for each country, and that'll give us our expected counts under the large sample. So that's what we will do when we get to the plan section. So now going to the plan section, random, it's a simple random sample of 200 kids from the UK, and simple random sample of 215 kids from US. Okay, so for the large sample, this is what I mean that you have to list every single one, even if they're the same. They're obviously not going to be the same for this one. So take each of those proportions. So for fly, you would take the 0.24 and you would multiply by 200. So we're going to do UK in one column, and then we'll do US in the other. So that's 48, and that's greater than or equal to 5. And then you take the proportion, the expected proportion for freeze time, which is 0.23, multiplied by 200. That's 46, which is greater than or equal to 5. Invisibility, 0.16 times 200. 32 is greater than or equal to 5. Super strength, 0.10 times 200. That's equal to 20, greater than or equal to 5. And lastly, 0.27 times 200, which is 54, which is greater than or equal to 5. So that's for the UK group. Okay. For the US group, take the same expected proportions, 0.24, and multiply by its sample size. That would be 51.6. And remember, it's okay to have decimals because I rounded when I was doing those proportions. Okay, and then 0.23 times 215, whatever that is. And we can't just say whatever that is. We need to write down what it is. I just said that. So 0.16 times 215 equals 34.4, which is greater than or equal to 5. This takes so long. 0.10 times 215 equals 21.5, which is greater than or equal to 5. I had a student tell me that he will not just list one of them in the near future, because if he does, the whole class is going to get a really, really tough test. So 0.27 times 215 equals 58.05, which is greater than or equal to 5. So large sample is met. And then finally, for the independence condition, it's reasonable to assume that there are more than 2,000 kids in UK and more than 2,150 kids in the US. All right, in our do, we are going to find the chi-squared statistic. So the chi-squared statistic, let's list out the first two. Now, if we go over here, let me go back over here. 54 is what we, so 54 is what we observed, but what we expected was 48. That's what we found in the large counts. And for freeze time, we observed 52, but we expected 46, and so on. So you might want to write those numbers right next to each other, or just look at your large sample. So when doing this, our observed was 54, but our expected was 48, squared divided by expected. For freeze time, it was 52. That was observed minus 46, quantity squared, over 46. And of course, you would have to do this 8 more times to have the UK and the US in there. And we don't want to do that. So we'd plug in those numbers in our list. And when we do, we end up getting a chi-squared statistic of 6.291544886. Okay, so we would do find the probability of getting a chi-squared greater than 6.29. We do a chi-squared CDF, or a lower bound is 6.29. Upper bound is something large. And our degrees of freedom. So let's take a look here. For degrees of freedom, we have 5 responses. We have fly, freeze time, invisibility, super strength, telepathy. So subtract 1. So that's what I meant by column minus 1. Times the row, we have UK and US. So that's 2 minus 1. So that's 4 times 1, which is just 4. So your degrees of freedom is 4. Okay, put that in and you get a p-value of of 0.1785. Compare that to alpha is not less than 0.05. Since our p-value is not less than 0.05, we fail to reject the null hypothesis. We do not have convincing evidence that there is a difference in the distribution of superpowers for kids from the UK and kids from the US. So follow-up don't have to do because there was no difference. Okay, now for the chi-squared or two-sample z-test, when dealing with two categorical variables that each have only two categories, so when we're dealing with a 2x2 table, we can use a chi-squared test or a two-sample z-test. The p-values will be approximately the same, and any differences will come from rounding errors. So I do want to do an example in that kind of situation. So in a study reported by the Annals of Emergency Medicine in March 2009, researchers conducted a randomized double-blind clinical trial to compare the effects of ibuprofen and acetaminophen plus codeine as a pain reliever for children recovering from arm fractures. There were many response variables recorded, including the presence of any adverse effects being nausea, dizziness, and drowsiness. Here are the results. So row 1 lists the adverse effects for ibuprofen and acetaminophen plus codeine, and then row 2, no adverse effects. And then you have your totals. So this is a 2x2 table, and here we have our responses. So either adverse effects or no adverse effects. And here are our explanatory variables. Okay. And what you want to do, since we don't have to graph it, we don't really need to look at the conditional distributions, but we want to do the marginal distributions. So over here, so looking at these, we have 93 divided by 234, which gives us 0.3974. And we have 141 divided by 234, which gives us 0.6026. Okay. Is the difference between the two groups statistically significant? Conduct an appropriate chi-square test to find out. We want to perform a chi-square test for homogeneity at a 0.05 significance level. There are null hypothesis. There is no difference in the proportion of patients that had the response variable, so adverse effects when taking ibuprofen or acetaminophen plus codeine. Our alternative, there is a difference in the proportion of patients that had, again, the response variable, so adverse effects when taking ibuprofen or acetaminophen plus codeine. Checking the conditions. This one is not a random sample, but is a random assignment. It's an experiment, so we want to establish cause and effect. So random assignment of 234 kids. For our large sample, we are going to look at those expected proportions. So for the ibuprofen, it'd be 0.3974 times 122, and that gives us 48.5 is greater than or equal to 5. And then take 0.6026 times 122, and that gives us 73.5 for no adverse effects. So, and if you want to, you can put them right, like I said, some students just like to list them right next to these. And then you have the observed, and then you have the expected listed right next to it. Okay, and then we're going to do the same thing for acetaminophen plus codeine. So 0.3974 times 112, it's 44.5, which is greater than or equal to 5. And then 0.6026 times 112, and that is 67.5, which is greater than or equal to 5. I'll put those right here. right, and those are all met. Might as well just put the degrees of freedom too while I'm thinking about it. So the degrees of freedom, you have two responses, so 2 minus 1. And for the explanatory, you have 2 minus 1. So 1 times 1. Okay, so our degrees of freedom is 1. And our independent, so the random assignment assures independence. And honestly, the fact that it's double blind, it keeps the independence because you're minimizing as many other variables as possible when you're doing a double blind study. So double blind keeps independence. All right, and now for our due portion. So for our due portion, our chi-squared statistic is equal to 36 minus 48.5 quantity squared divided by 48.5 plus 86 minus 73.5 quantity squared divided by 73.5 plus, and so on. And again, I put all of this in my list, and that gave me a chi-squared statistic of 11.17. So our probability of getting a chi-squared greater than 11.17 is equal to chi-squared CDF lower bound 11.17, upper bound 1,000 or 10,000, something, just put some zeros there. And our degrees of freedom equals 1. So our p-value ends up being, well, this is what our calculator is going to show, 8.3 times 10 to the negative 4th. So I'm just going to write that as a decimal. So 0.00083, which is less than 0.05. So since our p-value is less than 0.05, we reject the null hypothesis. We do have convincing evidence that there is a difference in the proportion of patients that had adverse effects when taking ibuprofen or acetaminophen plus codeine. And I'm not going to ask you to do a follow-up, but we would go and analyze the L3 and see which components contributed the most, but we're not going to do that. We are actually, in part B, going to calculate the two-sample Z statistic and the p-value, and this is what we did back in Unit 6. What do you notice? So when we did a two-sample Z statistic, or in differences, we listed the null and alternative hypothesis. So in this case, the PI would be the ibuprofen, and the PA would be the acetaminophen plus codeine. So the null hypothesis is there is no difference. The alternative, there is a difference. So it's a two-tailed test right there. So remember, when you're doing your p-value, you remember to multiply by 2. So our, and we're just dealing with adverse effects. So adverse effects for ibuprofen would be 36 divided by 122. So that's our proportion, and that is 0.295. And for acetaminophen, it's 57 over 112, which is 0.509. And then we pool our values together. And so we have 36 plus 57 with adverse effects over the sample sizes of 122 plus 112. And so that gives us 93 over 234, which is 0.397. And we need that when we're doing our z-score. So now to calculate our z, that is equal to P1 or PI, which is 2.295, minus PA, which is 0.509, divided by our standard deviation, which is 0.397 times 1 minus that, which is 0.603 over the first sample size, plus, oops, didn't make that big enough, okay, 0.397 times 0.603 over the second sample size of 112. Yes. And so that the numerator gives us negative 0.214, and the denominator gives us 0.064. Divide that, and you get a z-score of negative 3.34. And then you want to do a normal CDF because this is for proportions and it's a z. So, and hopefully you'll see what I'm doing. Always look back at your alternative hypothesis. This is two tails, so you want to do a two normal CDF. And our lower bound can be something like negative 1,000. Upper bound is negative 3.34. And our mean is 0. Standard deviation is 1. And that gives us a p-value of 0.000826665, which is pretty close to this right here. So you could have used either test there if you have a 2x2 table. So you can use the chi-squared test or the two-sample test. So the chi-squared test for homogeneity or the two-sample z-test. And in 11.2b, we will do our last chi-squared test, and that will be the chi-squared test for association or independence. Have a great day, AP Stat students.